Hello and welcome back. I just checked my email and got a question about 1C that I thought I would talk about on the homework rather than replying to that email. And today is pretty exciting. We're going into birth and death processes. And these are where you have populations and people coming in and people leaving. And that's exactly what you need in order to talk about queuing processes, which is, servers and customers and lines and packets of information. So it's going to be cool. So this is homework 7, and if you didn't, a lot of you don't read or don't get any of the announcements I put on Canvas, but you should check there from time to time. Your homework has just been extended a week, and I'm not assigning anything new during this lame spring pause. So in 1C, let's see, we had customers entering a bank, and it was lambda equals 30 customers per hour. And then 60% of them were there for a checking account transaction, 30% for a savings account transaction, and 10% for a mortgage transaction. So we can thin those into individual Poisson processes. Okay, so if you let N1 of T be the number of checking transactions. Okay, so the number of checking customers by time T, and then N2, same thing for savings, and N3 of T is mortgage transactions. Okay, and in problem 1C, we want the expected number of savings account transactions to happen before the first checking account transaction. So the N1 of T is its own Poisson process with rate lambda 1 equaling the probability that something is a checking account transaction times the overall rate. And so that is 0.6 times 30, and that's going to be 18. And then N2 is a Poisson process with rate lambda 2 equals 9. And 3 is a Poisson process with rate lambda 3 equals 3. So this is just another thinning and superposition problem. And anyway, my question was about C. Expected number of savings account transactions to happen before the first checking account transaction. To happen before first checking. So there's many ways you can do this. And some of you have talked to me already about some common sense approaches, which I think were well explained, and I will take it. If you're going to do a more mathematical approach, though, what I would do is I would get rid of the mortgages, and I would consider a Poisson process. I'm going to call it N tilde of T, where it is defined to just be the checking and savings account processes added together. And so this is a superposition of Poisson processes, and this is a Poisson process with rate, I'll say lambda tilde, which is lambda 1 plus lambda 2, which was 18 plus 9, or 27. One way you can do this, I'm not actually going to write this because it's taking too long already. So method 1 would be to say, you remember from the bug problems, what is the probability the next event is a checking account transaction? So the probability the next event is a checking account transaction is the rate of checking versus the overall rate, which in this case is lambda 1 plus lambda 2, because we've kind of ignored the mortgages. And so you could compute C as the expected value of a geometric random variable, where the trials are the different transactions, and you call savings account transactions a failure and checking account transactions a success. You want the expected number of failures before the first success. So one way to do this is with the geometric. Another way, which is, I don't think is to compute the probability that the expected number of savings account transactions. Oh, so I don't want a probability, I'm so sorry. I want an expectation. The expected value of N2 of capital T, where capital T is exponential with rate 18. So it's the next time to a checking account transaction, and you want the expected number of savings account transactions in the time it takes for one checking account transaction to occur. So you can condition on the value of T and do it that way. And like I said, some of you have some pretty good common sense arguments for what you think it is. And as long as you put some explanation around it, I'll take it. All right, so let's talk about new stuff. Birth and death processes. In particular, we're going to start with birth processes. And this stuff is going to rely on your homework problem 2. So number 2 on the homework, I just want to state here, says that if you're looking at something like 1 minus lambda h to the I, that this is 1 minus I lambda h plus little o of h. And I did recommend last time that you prove that using the binomial theorem to expand out the left-hand side. The next thing you have to show there is that lambda h plus little o of h to the I is lambda h to the I plus little o of h. And the final thing to show is that 1 minus lambda h plus little o of h is, when raised to the I minus 1 power, is 1 minus I minus 1 lambda h plus little o of h. So I would use binomial theorem, and then A plus B together to make C. And the reason I wrote such weird things like, why did I use I's and what's with the I minus 1 is for what we're going to do today, which is to talk about birth processes. So a birth process is a kind of counting process like a Poisson process, but the arrival rate can vary, not depending on time, but depending on the current number of people in your population. So that's why we think it. I don't think that would make it 1/8. I'm just reading the chat. Because this is not the mean of the exponential, it's the mean of the second Poisson process when conditioned on the exponential. So you would have to say this is the integral from 0 to infinity, expected value of N2 of little t. Well, I'm skipping a bunch of steps here, but t given t equals t times 18 e to the minus 18 t dt. Okay, so sorry, that was just a chat question. A birth process is like a Poisson process, but we get the arrival rates to be able to depend on the number of people in the population. And this doesn't have to be a population of people. It could be really counting anything, but here is the definition. So I'm going to let x of t for t greater than or equal to 0 be a stochastic process. That's just a random process that evolves over time. And I want it to have state space 0, 1, 2 on up. And so it's called a birth process if a couple of things hold. So x of t, you notice I'm not using the n anymore. The n this is also a kind of counting process because it's only going to be able to go up, but the n is usually reserved for the Poisson process. So this is another type of counting process. But we say that x of t is a birth process if it is a Markov chain or a Markov process. And we have the, I wanted to say something else in there. If it is a non-decreasing Markov chain or process such that we have the probability of incrementing up by 1 in a small time interval of length h, given that we currently have I people in the population, So this is something we looked at for the Poisson process. And in the Poisson process, what happened here was completely independent of this. But it's no longer completely independent because having currently I people in the population gives us a rate. So it looks like a Poisson process. So it's a lambda sub I of H plus little o of H. So these are no longer constant. That's the only thing that changes. So you can imagine these are not processes where they're actually like couples giving birth. It's one person to one child, and it's more like splitting particles in physics or biology applications. So if there's I people in the population, then there's I people there that could possibly give birth in the next little increment of time. And these lambda i's are known as the birth rates for this birth process. And to fully define this, I need to give at least one more condition. So I'm going to go with the one we used for the Poisson process, greater than or equal to 2 events in any tiny time interval is little o of H. And these statements only make sense if I include up at the top as H goes down to 0, because if someone were to walk in and see you doing that with an H there, they could think that's a generic time increment. And actually, I guess it's still right, but then you would have actual interesting probabilities and not just the little o stuff, which is to describe what's going on in a tiny interval. So we get a third condition automatically. You could state any two of these to have a birth process, and that is that the probability of 0 arrivals given arrivals or births, this is 1 minus the sum of these other two things, which turns into a 1 with a little o of H finagling algebra, arithmetic. This is 1 minus lambda sub IH plus little o of H. And so there's 3 conditions, but you only need to specify any 2 out of those. So if the lambda i's are constant, then it is just a Poisson process. The lambda i's are known as the birth rates of the process. And specifically, lambda sub I specifically is the birth rate at the time the current population size is I. So what a mess for a new definition. I just want to go to an example though. Any questions on that? I mean, I think if there are, they'll be cleared up in this example. It's just another definition like the Poisson process, but the lambda is allowed to be a lambda sub I, and it is important to keep this information. Whereas before, this was completely independent of what happened before it. Also, we don't have conditions that make this something that you can prove that is a Markov chain. Saying that it's a Markov chain is actually part of the definition here. Whereas we got that out of the I, double I, and triple I for the Poisson process. All right, let's do an example. But in a non-stressful way, because we are in spring pause. Okay, so this is called a linear birth process, which is also known as a Yule process. Yule was some dude who first postulated linear birth processes. So I want to try to slow down and start writing neater. Here's the setup. We have a population, which doesn't have to be an actual population of organisms, in which no individual can die. I was saying before that these are used to model things like cell division. This one in particular is used to model cell division all the time, where you have a cell and then suddenly you have 2 cells. So no individual may die, and each individual acts independently of everyone else and the population size and everything else in giving birth to a new individual in a small time interval of length h with a probability that I'm about to write down. So each individual acts independently . in giving birth to a new individual in a small time interval. So from t to t plus h, and they do so with probability lambda h, and yes, I mean lambda, not lambda I, plus little o of h. It's just that when we consider the population as a whole, we're going to have all the individuals kind of racing to be the first one to produce a new cell. And so that's where the birth rate is going to come in and not be exactly lambda. And assume that multiple births aren't allowed, twins aren't allowed, triplets aren't allowed, and that the time interval is so small that you can't even have multi-generational births. So the offspring of a particle cannot produce another particle in such a small time interval. So assume that h is so small, can't have multi-generational stuff. I guess can't is not the right word, but that it's really negligible and it's going to be a little O term, and no individual has multiple offspring at once. This would have been better to pre-write. I agree. Okay, so I'm going to let x of t be the population size at time t. And I want to show that this is actually a birth process. So I want to show that it satisfies that definition we had with the lambda sub I of h and the little o's, and I want to identify the birth rates. So that's the goal. Show this is a birth process and identify the birth rates. Okay, so I need to take any 2 out of 3 of those probability statements and write them out and hopefully get something in the right form and then peel out the birth rates. So if you want to, let me write down more than just one at a time. We can look at the probability that the population size in this tiny interval increases by k. So k here could be 0, 1, 2 on up, given the current population size is I. So the way this would be computed is out of the I individuals, you have to choose K. We're looking at such a small interval of time that no one individual can have multiple births. So this is really out of I individuals, you have to choose K in the population to give birth. This is the probability exactly K individuals give birth in the time interval t to t plus h plus little o of h. So this is here to wrap up the other possibilities that one individual gave birth and then gave birth again really quickly, or there was a multi-generational thing. And so that's part of our assumption in setting up this process, that that stuff is negligible. And this would be out of the current I people in the population, you have to choose K of them to give birth. And so we're just going to say like success is giving birth and failure is not giving birth. And the probability of success, the probability any one person gives birth is lambda h plus little o of h to the kth power, and then 1 minus lambda h plus little o of h to the I minus k, plus the other little o of h, which already takes care of the negligible stuff about multiple births and multi-generational things. But I don't really care about this for a generic k. I want to find the birth rate. So let's look at it when K is 1 in particular. Population size at time t plus h minus the population size at time t. So this is the amount the population increased in this tiny interval of length h, given the current population is I, is just the formula I just wrote down, but specifically K is 1. So out of I people, we have to choose 1 to give birth. Any 1 gives birth with probability lambda h plus little o of h. So we get that to the 1. We get the remaining probability. And yes, it's not minus little o of h. That's just how the notation is. It's just wrapping up the extra stuff. Although technically you could write minus little o of h to the I minus 1 plus little o of h. And if we write this out, so I choose 1 is I, lambda h plus little o of h is, it's to the first power. So let me get rid of the power. And the next term is 2c on the homework. And now I don't regret it, but pushing off the homework another week, I don't really want to keep using these facts for a whole week without you having seen them. So I might break down in the next class and do some problem 2. But by homework 7, problem 2c, we have rewritten this as 1 minus I minus 1 lambda h plus little o of h. So we went from here to here by problem 2c on homework 7. And then I still have the final little o of h hanging out at the end. Right, let's multiply this stuff together. There's an I sitting out front, and this is not an imaginary unit I. This is the current population size, and it's really common to use an I, so I didn't do it to be confusing. I did it to use common notation. If you multiply these two things out, the first thing you get is lambda h times 1. And that is not a little o of h term, because if you divide that by h, you get lambda, and that should go to 0 as h goes to 0, but it's not going anywhere. So we get lambda h, and then I'm going to use a different color. Lambda h times this has h squared in it, and that is a little o of h term. And anything with powers of h, 2 or higher, definitely little o of h. And lambda h times little o of h, remember, if you take a little o of h function and divide by h, that is not necessarily little o of h, because you could have had like an h squared. And if you divide by h, you only have an h. And that's not little o of h, because if you divide by another h and let h go to 0, it doesn't go away. But something that's little o of h times another factor of h is even more little o of h. So the two circles in yellow, little o of h. This is so messy. Little o of h times 1 is little o of h. Little o of h times a constant in front of an h is little o of h again. Think of, they're not always polynomials, but you'd be fine to think of these little o of h things as always polynomials with degree 2 or higher. And in fact, everything else here is little o of h. And so if we multiply this out, we get I lambda h plus, so I times little o of h is still just little o of h. And so we got our first probability, which was that we were incrementing by 1. And so if this is in fact a birth process, and we need to show at least one more condition to show that it is, then we appear to have our birth rates. The lambda I is supposed to be the rate of birth when the current population size is I, and that is the thing in front of the h. So it is I times lambda, where lambda was the constant rate for any one individual. So what can I clear up? Anything? Okay. Okay, I guess we didn't prove it was Markov. I'm not going to mean for you to do that on the homework or the exam either. To show it's a birth and death process, I really just want you to show the 3 conditions or 2 out of the 3 conditions and identify the birth rates and what's coming up, the death rates. So usually at this point, like in the Poisson process, when I want to verify another 1 out of those 3 conditions, I go to the greater than or equal to 2 condition because I think it's more easily interpretable. But if I did that here, it's a little harder because we're going to have to add up all sorts of things. So I'm going to go for the increment of size 0 condition. So let's check it out. The probability of going between times t and t plus h of incrementing by 0, given there's currently I people in the population. This is just the probability that no one gives birth in that time interval. Now, once we introduce deaths into the population, it could be that no one gives birth or one person gives birth and one individual dies. And that's 2 things happening in a really small time interval, but without any assumptions about it, that's what you have to assume. And we'll see that that part actually turns out negligible. So xt is I. Right, so out of I people, we have to choose 0 to give birth. The probability anyone gives birth is lambda h plus little o of h. We get that to the 0 power. Then we get 1 minus lambda h plus little o of h to the I minus 0 power. So I choose 0 is 1, this is 1, this is 1, and the rest of it is that thing to the I. So I can again use problem 2c with an I instead of an I minus 1. So this is problem 2c on the homework. This is 1 minus I lambda h plus little o of h. We would be in trouble if this was anything but I lambda, because by definition of a birth process, excuse the scroll, come on, where was that? Oh, way up here. By definition of a birth process, we have to see some kind of lambda I in the case where the change in population was size 1, and we have to see 1 minus that exact same lambda I times h in the case where the population size was 0. So if you somehow did not get I times lambda, which is what we saw for our lambda I, then either you did something wrong or it's not actually a birth process by definition. So this just checks out. And so assuming it's Markov, which it's pretty easy to make an argument that it is, you know, there's nothing going on where maybe the birth rate could depend on the population size. We could have something where the population is just too large and there's no more births. There's some kind of natural selection thing going on and thinning of a population. But it certainly doesn't depend on anything that happened before that time. So the description is very Markov. Questions?
Jim, if we could just zoom back out while listening, I didn't take any notes, just if I can take a screenshot of it, please. Thank you. I think a little bit more to the top.
Okay, so let's do one more linear type birth process, but let's allow immigration into our system.
Thank you.
Okay. Oh, up again?
Sorry about that. No, just scroll down. Thank you.
Okay. So my second example and my last example for today, because we're on spring pause and we're kind of chilling and being light about this, is a linear birth process with immigration. With immigration. So this is just going to be the birth process or Yule process, but people are coming in from outside of the population with a constant rate. And I'm going to call it, since I already used up lambda for the linear birth process, I'm going to call that constant rate nu. So let me write this down. this is a linear birth process. And additionally, individuals migrate in at a constant rate that I'm going to call nu. Additionally, individuals migrate in at a constant rate mu. So you can make this much more interesting by having the rate somehow depend on the current population size. Like people are like, there's way too many people, I'm not going there, kind of thing. A constant rate nu. But in this case, the rate of immigration is not depending on the current population size. So this is, first of all, I should tell you exactly what is meant when people write something like this. This means this actually means, the definition of this is the probability an individual arrives in a tiny time interval from t to t plus h. Well, you know what this means, actually. This is a Poisson process. The constant rate thing is like a birth process with a constant rate, and that's a Poisson process. So that means that the probability of one arrival in a tiny interval of time is going to be nu times h plus little o of h. And it means the probability of greater than or equal to 2 arrivals in a little interval of time is still little o of h. So I guess that's what I should have written. By this, additionally, individuals migrate in means a Poisson process, a constant rate process that you're adding to the population with. Right. Okay. Really low energy. I don't know why, because this is awesome. This is one of my favorite parts. Also, it is spring pause. All right. So hold on. Mute. All right, let's go. You know, I told you last time about my karate competitions, and I would always have my coach smack me hard in the face before I went out because I would always start off kind of lazy until I got hit, and then I would like start fighting. So I wanted to be hit before every match. Okay, so let's check it out. Is this a birth process? And if so, what are the birth rates? So let's look at the probability that we increment by 1 when the current population size is I. And so we've already talked about these individual processes not allowing multiple births in a tiny time interval and not allowing multiple immigrations in a tiny time interval. Yeah, that was a nu, which is like a curly-ish V. But we haven't said anything about whether you can have a birth and an immigration in a small time interval. We do have to consider that. Now that will turn out to be negligible, but we don't know that at this point. So this is the probability of, I should label this stuff. I don't want to write out these words. All right, B for birth and I for immigration of one individual into the population. So this is the probability of 1 birth and 0 immigrants in T to T plus H, given the current population size is I, or the disjoint event, the probability there are 0 births and 1 immigrant in T to T plus H, given the current population size is I. And I guess I don't have to be concerned with what I was just talking about here. Now, if I was looking at an increase in size 2, I would consider the probability that there was 1 birth and 1 immigration, because as of now, I'm not sure that that's little o, but that would turn out to be little o. So let's just finish what I started though. These are disjoint events. That's why they got the addition between them. There should be a little o on the end, which takes care of all the other stuff that we're assuming can't happen. And then we have, oh, did I write that? I didn't write this, so this is super important. the immigration process. People are migrating in at a constant rate nu, and this is independent of the current state of the process, which is kind of said because the rate is constant and not depending on I, but I really do need to say it. The current process. So what I'm trying to say is this event and this event conditional on this, these are independent. So we get to break this up. This is the probability, one birth, when the current population size is I, times the probability of 0 immigrants coming in, given the current population size is I, plus blah, blah, blah. One immigration, given the current population size is I, plus negligible stuff. I guess we don't have to worry about that here, the negligible stuff. It's going to matter when we introduce death, because increasing by 1, let's say there was just birth and death, no immigration or anything like that. Increasing by 1 could mean that you had 1 birth, but it could mean you had 2 births and 1 death. And it could mean you had 3 births and 2 deaths. And so there's many ways to increase by 1. And this is going to become much more important when we talk about birth and death processes. But continuing, if the current population size is I, the probability of 1 birth is out of those I people, you have to choose 1 to give birth. So that is I choose 1. This is our linear birth process alone, like without the immigration. That part is separate now. And the probability that any one individual gives birth is lambda h plus little o of h. And that's to the 1 power. And then we get 1 minus lambda h plus little o of h to the I minus 1. I need to definitely make some new space here. This is going to be really hard to read as it is. So that gets multiplied by the probability of 0 deaths, right? Yeah, 0. So that is not dependent on a population size. The probability of 0 arrivals in a Poisson process with rate nu in a tiny time interval is 1 minus nu h plus little o of h. That's our condition for, did I lose this because it was messy, or did I lose another I? This I minus 1. Yeah, okay, thanks. So this is just the probability of 0 arrivals in a tiny time interval of length h when you have a constant arrival process. It's the same as the probability of seeing 0 arrivals in a Poisson process, which comes from definition 3, part III. Plus, so now I have 0 births. Out of I people, I have to choose 0 people to give birth. The birth probability to the 0, 1 minus the birth probability to the I minus 0, and that whole thing gets multiplied by the probability of 1 immigration, which is nu h plus little o of h. It's at this point when you realize how happy you are to have the little o's, because hardly any terms survive here. So I would look at the both individual terms in the sum. And in the first one, this is simply I. And I guess I need to write more. So this comes out to be I, and then lambda h plus little o of h. And then the last term, I'm going to use problem 2c again on homework 3 to rewrite that as 1 minus I minus 1 lambda h plus little o of h. So again, I'm using that simplification on homework 3 problem 2c. Plus, what's going on down here? This is 1, this is 1. So I have this, and using problem 2c on the homework, that is 1 minus I lambda h plus little o of h. And the whole thing has a plus little o of h on the end that I forgot to carry through. So, yep, what are we going to have here? When I multiply across the top, I get the lambda h times the 1, which is not little o of h. And I also get that times the I. But if you look more carefully at the other terms, they are all going to be little o of h terms, like the lambda h times the I minus 1 lambda h is going to be stuff times h squared, and that's little o of h. And everything else we've already talked about, actually. So this is going to simplify to I lambda h plus little o of h plus 1 minus I, oh, I lost my last term. Or did I already take care of it? I lost both of my. Arg. I'm so sorry. Okay, the very next thing I'm going to write down is this. And then I'll circle it in green. So this is going to be I lambda h plus little o of h, and then 1 minus I minus 1 lambda h plus little o of h. So that is the part that I have written with a green box around it. And then I get this. So that has to be on the end here, times 1 minus nu h plus little o of h. Then I get to the addition, and I get 1, 1, and then I rewrite this using 2c. This is 1 minus I lambda h plus little o of h, and that gets multiplied by nu h plus little o of h. And the whole thing has this little o of h hanging out on the end. And so what do we have? We've got what survives out of the top. So we've got a bunch of things to multiply, and I'm not going to multiply these all out. But if you take this times this times this, that is not little o of h. That has just h to the 1. And that all gets multiplied by I. So this is I lambda h. And then I claim the rest of the stuff in that top line is all little o of h. It's all powers of h higher than 2 or higher. And then below, oops, I get the 1 times the nu of h, and that is nu of h. The 1 times the little o of h is little o of h. The I lambda h times nu h is an h squared term, which is little o of h. They're all little o of h from there on out. So we get I lambda plus nu times h plus little o of h. And this is shaping up to be a birth process with the birth rate, or rates, since they hold for any population size I, lambda I is I times lambda plus nu. It still looks complex. It's not. And to finish proving that it is a birth process, we need to look at one other thing. And so nu h, where did we get that from? Depends on where you're asking. It came here from this 1 times this nu h term. It's hard to see in my big mess here, but I don't know if you want to know who asked that. I don't know if you want to know where it came from further back. Let me know. Right, so to verify that it is actually a birth process, you need to look at one more other condition. And I'm going to spare you that. You can read it in the notes. I meant to end earlier than this for us to feel like we're on spring break. Woo, this is great. So actually, I already have these written. I have just rendered my last video. I'm going to catch up on everything right now. And yeah, happy spring pause. So what else should we talk about? Or that one more if it still doesn't make sense?
I had a question about finishing 3. I got through most of it, and then I feel like I got stuck at the end. I still have a CDF, even though we didn't use the CDFs. So maybe I did something wrong.
So did you start with a PDF as suggested?
Yep.
Okay. So if you let X be the output of the algorithm, then you want to look at the probability that X equals X, and hopefully it is the given PDF or PMF. So I would start off the same way. I would sum over N the probability that X equals X, and the first except, and really the only except on the nth trial. So just like before, this is the sum as n goes from 1 to infinity of the probability of n minus 1 failures, which yes, can be written out with n, y1 through yn and u1 through un, but it turns out not to be important, just like it wasn't in the other proof we did. And then the success on the nth trial means the nth y you draw. If the output is going to be x, then the nth y you draw is x. And the nth uniform is less than or equal to f of this yn over gn, g of the yn. And so this is independent of that because all our x's, all of our y's and u's are independent of each other. So you do get to factor. This is the sum, n goes from 1 to infinity, probability n minus 1 failures. And then probability yn is x. I see what you're saying, though. I can see where that sum is going to come in. So then looking at that last piece alone, the probability that yn is x, and oh, no, yeah. Actually, yeah, this is much easier. So looking at this last piece, I was about to condition on y, which probably is what you did and where you got that sum that looked like a CDF. But in this case, we actually know the exact value of yn, whereas in the in-class example, we only knew that it was less than or equal to x, and we didn't know the exact value. But since we know the exact value is x, this is the same thing as the probability that yn is x, and un is less than or equal to f of x, g of x. Like no integral or sum comes in there. And it had to come in last time because I didn't know exactly what it was. So yeah,
that's what I get for just copying your proof and changing it and not.
I almost did it too, though, because I wanted to, condition on what y is, but I already know what y is. And for anyone else, I realize you got it. We just clean this up by saying that doesn't do anything. So at this point, putting everything together, we have the probability that x equals x is the sum as n goes from 1 to infinity of the probability of n minus 1 failures. And then, like, independent of that, we've got the probability that yn is little x and un is less than or equal to f of little x over g of little x. And then you get to factor this probability. And the first probability is what we're calling h of x. And the second probability is exactly like it was in the in-class example. The probability a uniform is less than or equal to a number less than 1 is just the number, right? The probability that a uniform is less than or equal to some x is just x if x is between 0 and 1. So we get f of x over g of x. And yeah, everything should start going away then, because the g of x is a multiple of h of x, so you'll get some cancellation there. And then after canceling that, I would sum both sides as x goes over everything. And the left-hand side summing over all x would be 1, and this guy summing over all x is 1. So you can again prove that this sum times 1 over c is 1, or times c is 1, exactly what we did last time. And I'll go into more detail if anyone cares, but I've just been talking and talking and no one actually asked me to go further.
Jim, could we zoom out a little bit so I can capture that? Thank you.
As an aside, do you know when the grad exam will be graded? If you don't, that's totally okay.
Seriously, it's not because you just said this. I'm gonna get on it today because I was grading that. And like I said, I had this Coursera deadline, which is not your problem, but I had to finish a course this weekend. And it
No problem.
It took
Yeah,
up my
there's no
last
rush,
2
I was just
weeks.
wondering.
So yeah, I'm gonna get on that like
Cool.
today.
Thanks.
Sorry, Jim, I realize I might be getting annoying at this, but could I get that
No.
last? I wasn't sure what was there. I can't see.
That part?
Oh, that's just a point that you raised. And there was also, I think it was if this is the last problem we worked with, not the one before it, the one before that. I didn't catch the notes. It was basically the one that started off with each individual act independent.
Yeah, I know where that is. That's, I think, this linear birth process. Each individual acts independently in giving birth to a new individual.
Yes, that's correct.
Since I'm cutting off slides anyway, let me just make this large and give you each one.
Okay, I can do that. I think I got that, and I got the
Okay.
one, if I'm not mistaken. Yep, I've got all the way up to where you have the probability exactly. I think up again. Sorry. Yeah. Yeah. You were right. Next slide. Sorry. Yep. You're right. Perfect. Thank you. And if I could just take the next one too, please. Thank you.
So, other questions?
I think if that's
Oh,
it.
sorry, I moved that probably while you were taking the screenshot.
I'm enjoying the challenge, Jim. No, I think.
It's
Sorry.
It's a stochastic thing, jumping around.
This is sarcastic thing, commenting.
Yeah.
Thanks again, Jim. All right, well, thanks again. I'll see you on Wednesday. Bye-bye.
Okay.
I was hoping to ask a question about number 4. I kind of started to play around with doing some simulations. I was struggling with, because you said not to use like the packages that allow you to like simulate like an exponential. And I just wasn't exactly sure how to do that.
Yeah, so the way we've talked about simulating an exponential is with the inverse CDF method. So if you have a continuous x with CDF capital F, we showed that the inverse of the CDF with a uniform plugged in, so let me say U is uniform 0, 1, has the same distribution as x. So this is a function, but we're plugging in something random. So the thing on the left is random. And we did the specific example that if x is exponential with rate lambda, this means that the CDF is f of x is 1 minus e to the minus lambda x. So if you call this y and solve for x, you'll get x is minus 1 over lambda, the log of 1 minus y. So that's your inverse function. So it takes 2 steps to generate an exponential. Step 1, grab from the random number generator a u. And step 2, the exponential is minus 1 over lambda log 1 minus u.
Okay, that makes a lot of sense.
Cool. And you know what? I never told people before because I don't know. I just moved on to other things. But 1 minus u has the same distribution as u. If you take a uniform number between 0 and 1, it's equally likely to be everywhere, anywhere.
Oh,
And 1
yeah.
minus u is still, so you could actually replace that with a u.
Okay, that makes sense. Okay, thanks. I think I have enough to do it now. I was just a little lost there.
Yeah. Okay, great. Cool.
Thank you. Have a good day.
You too.